All right, let's just dive right into this explainer and demystify that dense alphabet soup of GSM network architecture. If you're an RF engineer heading out to measure signal strength, cell reselection, and handover boundaries, you simply can't optimize what you don't understand, right? Today, we are stripping down the entire GSM network structure from A to Z, looking at the exact foundational 2G mechanisms that make mobile communication and subsequent network optimization even possible.
To keep things flowing, here's our roadmap for today. We'll start inside the mobile station, move on to the base station's subsystem functions, then hit the network switching subsystem core, check out the GSM security authentication elements, and wrap it all up with logical and broadcast channels.
All right, Section 1. Inside the mobile station.
You know, GSM architecture completely revolutionized mobile hardware by making sure the mobile station wasn't just one giant monolithic block, it's actually two completely independent parts. On the right, you've got the SIM, the subscriber identity module, that holds your identity, your subscription details, and all those essential security keys. And on the left is the mobile equipment, or ME, which is just the physical handset. This strict separation was a massive deal. It meant you could literally pull your identity out and pop it into a different piece of hardware. Honestly, that architectural decision profoundly shaped the entire history of mobile telecom.
Moving right along to Section 2, Base Station Subsystem Functions.
So, your first point of contact in the BSS is the BTS, the Base Transceiver Station. And look, it's absolutely crucial to remember the BTS is not just some dumb tower antenna passively bouncing signals around. No way. It is actively grinding through these critical, low-level, rapid-fire tasks. It's converting radio signals into a format the network can actually read. It handles ciphering to secure the air link, performs channel coding, interleaving, and it's doing the actual modulation and demodulation of your signal. Plus, it meticulously records signal strength measurements, which, if you're out doing a drive test, is data you are heavily relying on.
Then, moving just slightly upstream from the tower, we hit the BSC, the base station controller. Think of this as the local brain of the radio network. While the BTS handles the raw physics of the radio waves, the BSC is playing conductor for multiple base stations at once. It's constantly churning out power control and handover calculations behind the scenes. So, when you're doing a drive test and you seamlessly transition from one cell sector to another while cruising down the highway, yeah, that's the BSC calculating and executing that handover.
Next up, Section 3. We're diving into the network switching subsystem core.
This is where we meet the real heavy lifters of call routing. The Mobile Switching Center, or MSC, is your primary node here. It takes care of routing, service provisioning, and the all-important charging functions for calls going to and from the mobile station. But say someone from an old-school landline tries to call your cell. What happens? Well, that is exactly where the Gateway MSC, or GMSC, steps in. It acts as a bridge. The landline hits the GMSC, which then turns around and interrogates the network's databases to figure out exactly where on Earth your mobile device happens to be right now.
And it is super fascinating to compare those two databases directly. To route that call we just talked about, the network relies on the HLR and the VLR. Think of the Home Location Register, the HLR, as your permanent home address book. It's a centralized database holding global subscriptions and basic authentication data. The VLR, on the other hand, the Visitor Location Register, is more like your temporary hotel guest registry. There's one integrated into every MSC service area. As you travel around, the VLR downloads a temporary copy of your profile. That way, the local MSC doesn't have to constantly ping the global HLR halfway across the country for every single thing you do.
All right, that brings us to Section 4, GSM Security Authentication Elements.
So the really crucial point to grasp here is this strict division of labor between two totally distinct security nodes. It's honestly a brilliantly paranoid system that mirrors that SIM and handset separation we talked about earlier. First, you have the AUC, the Authentication Center, that verifies you, the human subscriber, to prevent unauthorized network access and manage ciphering keys. Meanwhile, the EIR, the Equipment Identification Register, is a totally separate database that authenticates the physical hardware itself. This dual-layer setup is what allows network operators to permanently blacklist stolen physical phones from accessing the network, even if someone pops a perfectly valid SIM card into them.
And finally, Section 5, Logical and Broadcast Channels.
Broadly speaking, the air interface is split into control channels and traffic channels. The traffic channel, or TCH, carries the actual payload, your actual voice conversation or data. But what's really fascinating from an engineering standpoint is how these channels dynamically optimize bandwidth. Depending on how heavy the network load is and the signal quality, the TCH can just seamlessly shift its channel coding mode right between speech full rate and speech half rate. This lets the operator squeeze even more capacity out of the exact same frequency spectrum. Pretty clever, right?
Let's break down how this actually builds a connection step by step on the control side. When you fire up your drive test equipment, it doesn't just magically connect. First off, it searches for the FCCH, the frequency correction channel, which blasts out a pure signal so the mobile can lock onto the BTS frequency. Then, step 2, it reads the SCH, the synchronization channel. That delivers the TDMA frame number and the base station identity code. It's only after locking frequency and getting that time sync that it moves to step 3, reading the BCCH, the broadcast control channel. This is the one broadcasting the general cell info, like your location area identity, max allowed output power, and parameters for cell reselection.
And look, this underlying structure is exactly why getting a grip on this dense GSM alphabet soup matters so much. When you're staring at your TEMS drive test software, measuring things like the level difference between hopping channels or tracking a complex handover between site sectors, you are directly observing these BTS, BSC, and logical channel interactions play out in real time. Grasping these rigid, foundational 2G mechanisms, it's absolutely required before you can even begin to do meaningful network optimization or figure out why a call dropped.
Which really leaves us with a fascinating final question. In the source material, we see drive testing procedures expanding out to UMTS parameters, things like the UARFCN for frequency identification and CPIH-RS-CP for common pilot channel power. So, as we evolve into 3G and 4G networks using entirely different terrestrial radio access technologies, how are these rigid, time-slotted 2G structures going to adapt? How does network engineering shift when we move from simply tracking TDMA frame numbers to actually measuring the received energy per chip in a UMTS landscape? That right there is the boundary where legacy engineering meets the future, and it's exactly the kind of puzzle you'll need to explore next in your optimization journey.